In a previous video, we explored direct variation and what it meant if two variables had a direct variation. In this video, we're going to look at inverse variation. Just to recall, when we were talking about direct variation, we connected this back to our understanding of ratio and knowing that two variables reduced to the same quantity, we saw that the general form of a direct variation, if we were talking about, let's say, y, and let's say x, we know the general form, if these two variables were directly related, could be written as y equal to k times x, or if we wanted to kind of flip the variables there, rewrite that for x, we could also write this as y equals k times, or x equal to k times y. Either one of these is, or could be used as a general form of a direct variation. The key point is to see that one variable can be found by, or is equivalent to, the product of the other variable times the constant of variation. The reason I'm showing you this is because this is going to be different for inverse variation. If you look at this problem here, so just informally, if we're looking at the hours of schoolwork and we're comparing that or looking at the relationship with the hours of free time, we can see that as the hours of schoolwork increase, as we go from 2 hours to 3 to 4 to 6, the hours of free time decrease. So immediately we see as the hours of schoolwork increase, free time is decreasing. That is not going to be a direct variation. We immediately know that's not going to be a direct variation because with a direct variation, we saw just very generally, as one variable increased, so did the other. The other way you could immediately see this is not a direct variation is by looking at the ratio of schoolwork divided by free time, and you see it's changing each time. I don't have to do a lot of mental math to see 2 divided by 12 is not going to be the same as 6 divided by 4. So immediately I know this is not a direct variation. So when you're told that, and in this example what we have is actually an inverse variation. And with an inverse variation, we are going to compare two variables, or look at two variables, and they have a very specific relationship. So before we jump into the general form, let's introduce variables. Let's let h equal the hours, or let's not use h because hours actually goes for both. So let's let s equal the hours of schoolwork. Hours of schoolwork. And we're going to let's say f equal the hours of free time. So in order to describe a general relationship between these quantities, we definitely want variables. So s will equal the hours of schoolwork, f will equal the hours of, I don't know what's wrong with me, free time. So not schoolwork, free time. Sorry about that. So s is going to be representing some amount of hours of schoolwork. F is going to represent some amount of hours of free time. If we know there's an inverse relationship between S and F, meaning as one goes up, the other goes down, we also know if there's an inverse relationship that the constant of variation is found by taking S times F. And this is that variation constant that holds. So if I look at S times F, that quantity, that product, is going to hold. So in this problem, the constant of variation k can be found by taking S times F. So one instance of S of schoolwork and free time, I see when there were 2 hours of schoolwork, so if I just use this column, there were 12 hours of free time. That means my constant of variation is equal to 24. So now what I know is this product, S times F, always needs to equal 24. That's how these variables are related. Their product is always equal to 24. And as you see here, that works. 3 times 8, 4 times 6, 6 times 4, that works. Now this is one way that we could express an inverse variation. We could also solve this for either S or for F. So if we take and solve for S, we divide both sides by f, we get 24 divided by f. Or if we divide both sides by s, we get f equal to 24 divided by s. So these are two ways that we could write this relationship. S is equal to 24 divided by f. F is equal to 24 divided by s. And very quickly you should see this is different. This is different from the direct variation. With the direct variation, we had the constant times the other variable. The constant times the other variable. With an inverse relationship, an inverse variation, we have the constant divided by the other variable. Let's look at a few other examples. In this example, we're told we need to find the variation constant and an equation where x varies inversely as x, and we're given an instant of y equal to 22 and x is equal to 0.4. Now this is a very abstract problem. It doesn't really have, we're not told what y equals. It's not, in the previous problem, hours of schoolwork, or x is not the hours of free time. It's just very abstract. We don't know what these mean. But as soon as we see the phrase inversely related, we see that y varies inversely as x, you should think to yourself, if I know these quantities are inversely related, then I can multiply them to find my constant of variation. The constant of variation will be found by taking the product of the variables. So when y is equal to 22, so if I plug 22 in for y, x will be equal to 0.4. So if you plug those quantities into your calculator, you will get 8.8. So what this is telling me is that my constant of variation, in this case k, is 8.8. I can write a formula then. I know the product of x times y for all other instances needs to equal 8.8. So depending on how I want to approach this problem, if I wanted to solve it for x or for y, rearranging this for x, I get 8.8 divided by y. And I get, if I were to solve this for y, 8.8 divided by x. So either one of these, you don't have to do both, right? Either one of these would be appropriate. You should start to see that while x times y equal to k is a convenient way for us to find the constant of variation, you're going to begin to see that these two expressions down here, x equals 8.8 over y and y equal 8.8 over x, these are what we're typically going to see as the general form. So just very briefly, if I told you that two variables t and q were inversely related, then you know the relationship between them would be t equals k divided by q, or you could also write q equal to k divided by t. These are the general forms where the constant of variation is being divided by, that other variable. Let's look at one more example that incorporates a little bit more of a concrete information as opposed to an abstract problem. Here we are told the time required to do a job varies inversely as the number of people, p, who work on the job. So I'm going to mark these. These are my variables. I have t is time, and it looks like time is going to be in days, so t is time in days. And I see p is people, so p is the number of people. I'm just writing that down before I continue. I need to address this. If it takes 180 days for 12 workers to complete a job, how long will it take 15 workers to complete the same job? A very common mistake is for students to set up a typical proportion to address this problem, but that's incorrect because a proportion is a direct relationship between quantities. Here, we're talking about an inverse relationship between these two quantities. So there's a couple ways that we can represent this inverse relationship. We know that a constant of variation for an inverse relationship can be found by multiplying the two quantities, right, t and p. And then the general forms, we know if t and p are inversely related, then a general form might look like this. Or we know that one of our formulas, if we don't have to find both of these, but one of the formulas might be, or would be, t, that constant of variation divided by p, or setting p equal to that constant of variation divided by t. So the first thing we would need to do to address this problem is to find an equation, find one of these formulas that actually maps on to this problem. And to do that, I can find the constant of variation by multiplying t and p. So all I need is one instance. I saw that if it takes 180 days, so when 12 workers were working, it took 180 days. So when there were 12 people, then the time it took to complete the job was 180 days. That's what we saw. These two, p equals 12 and t equal to 180, are connected. When there were 12 workers, it took 180 days. Knowing that, I can find my constant of variation. I know that t times p will equal my constant of variation in an inverse relationship. So t was 180, p was 12, and if we multiply those quantities, then we will get our constant of variation. So 180 times 12 is equal to 2,160. So I now know that for all other instances here in this problem, the product of t, the time, and the p, the amount of people, needs to multiply to give us 2,160. And I can plug that into my formula now, right? If I know t times p is equal to that 2160, and I rearrange that for t, I would get this. So depending on which formula you want to use, these are the two formulas, but you, again, don't need to write both. Either one can be used. These are the two possible formulas that you could have gotten by finding that constant of variation. And now we can address this problem. How long will it take 15 workers to complete the same job? So in that problem, 15 workers, p is equal to 15. There are now 15 workers. So if I plug 15 into either one of my newly found formulas, I should be able to find an equivalent time that is related to that. So I'm going to plug that into this formula. T is equal to 1,060. I know the number of people working is 15. So now when I take 2,160 and I divide it by 15, the time it takes, that quotient is 144. It will take 144 days. 144 days. Now, just like what we saw with a direct variation, there's actually a way to solve these with a proportion, and your e-text tends to take this approach. With a direct variation, one might think that you could use a proportion set up like this, where the time it takes and the amount of people for one job is proportional to the time it takes and the amount of people on a second job. But this actually is not correct. With an inverse variation, so I'm going to circle this and exit. With an inverse variation, we actually have the times and the amount of people kind of flipped. So you would have in an inverse relationship, instead of having P1 over T1, P1 and T1 would actually be on opposite sides there of the equivalent ratios. So we have an inverse relationship. We have these two T's, or if you want to look at it, the P's being flipped. But you obviously see that P1 and T2 are not being grouped, or P1 and T1 are not being grouped together. Neither are P2 and T2. And it should be clear if you multiply, you'll get P1 times T1 equal to T2 times P2, which makes sense. The product of the two variables will always equal the same amount. If this is confusing, by all means, please ignore it. You can still consider what are the variables. If it's an inverse relationship, you know how to find that constant of variation. You know the general forms, right? It's going to constant of variation divided by that second variable, and you can use that to solve the problem.